Good morning, guys. Hope you're doing well. We're going to go ahead and start on the VSEPR lecture. So this is based off of the information that we talked about before in bonding and dot diagrams and formal charge and resonance. So all of those things are going to apply to what we're doing today. We need to make sure that we're taking that into account. So I'm going to show you as we go through this how I arrive at the Lewis structures that you'll see on the slides. And then we'll talk about how we apply those Lewis structures to the tables that we've been provided. So hopefully that will clear up a little of the strangeness and confusion related to this topic. I'm going to go ahead and share, and I'm going to pull up my slides, and we're going to go from here. Okay, so what are we going to talk about today? We're going to talk about a whole bunch of different molecular geometries. That's what all of these are called. So, and we're going to talk about VSEPR, which is valence shell electron pair repulsion, and how that leads to the structures that we're looking at. So those are the main topics that we're going to be talking about. We're going to be using a lot of the skills that we've done for bonding and dot diagrams, resonance, formal charge to determine all of this, okay? So in order to do that, let's do a review. We're going to consider ClF3. We want to talk about the Lewis structure of that molecule, what are the formal charges, blah, blah, blah. So I'm going to go ahead and move this over here. I'm going to show you my whiteboard. And I'm going to say, okay, we want to draw ClF3. Move my mouse because that thing is driving me insane. So ClF3. Now, you might remember that chlorine is a halogen, so that means it has 7 electrons in its valence shell. F also has 7 electrons in its valence shell. And that means that we can then take, we have 4 of those, so this is my Cl, this is my F. Seven times 4 is 28 total electrons that we have to deal with in this particular structure. So 28 electrons. We're going to put chlorine in the middle, draw a fluorine around each of it. Around here, put the 3 Fs around it. So that's my first step. So I have a total number of electrons. Now I've drawn my base structure. And I draw one bond in between the chlorine and each of the fluorines. So that takes up 2, 4, 6 electrons that I needed to deal with. At least we have 22 electrons that I then need to distribute. The next thing we're supposed to do after we draw the bonds is to distribute around this stuff that's not in the middle to fulfill its octets. So we're going to draw 2 electrons on each side of this fluorine to give it a total of 8. So 2 in the bond, 2, 4, 6 from the lone pairs. And we're going to do that on each of the fluorines. So 6 times 3, because that's what I just did, is 18. That leaves me with 4 electrons that I then need to put somewhere. And that somewhere is going to be on the chlorine in the center. So I'm just going to stick them right here because I don't know where else to put them at this point. That's my structure that I have to deal with, okay? I don't have any ability to make additional bonds. I can't pull any of the lone pairs on the fluorine into the chlorine because the chlorine already has an octet in the structure that it has. So we wouldn't need to be doing any of that kind of stuff. So I have three bonds, 2 lone pairs on the chlorine. All right. So that answers that portion of it. Now, the next thing we're going to talk about is what is the electron geometry and what is the molecular geometry and what are the bond angles that we're going to be looking at. And I know you're looking at me going, I don't know how to answer any of those questions yet. Well, no, you don't. But that's where we're going to talk about this table that comes in. So let me see if I can get my... This is the table that was presented in this particular slide. I'm going to minimize that and pull up this other table, which is the one you guys will see on the test. Now, this is not in your exam handouts, but it will be given to you if you need it. I do not expect you to remember all of this. What we need to do when we look at this particular table is we need to figure out how many bonding pairs and how many non-bonding pairs we have. So these are our bonding electrons, right? These are our lone pairs, okay? So if I have, oh, bear with me, I apologize. How are you? I'm doing just fine. My daughter threw up in my car yesterday, so I'm having it detailed, but that's not a big deal. Nope, nothing we could have done about it. So there's no reason being mad. So I was it's a rental, so I wasn't looking forward to doing it, but I don't know that I have a choice. Yeah, well, I was supposed to get my car back yesterday, but we didn't have time to pick it up, so we had the incident in the rental. So, but it happens. Everything's good. I have a lot to do between now and the end of the term. Going from 2 classes to 4 has been a huge change, but it's just I didn't expect it to be this much this fast. It'll be fine. I mean, it's just more stress than I anticipated. No, but it's normal, and it just means I need to plan better next time, which I can do. So, yeah, yeah. How are you doing? Okay. Yeah. Right. Right. Yeah. Right. Yeah. Right. Sure. Yeah. Well, and I think it makes sense given that that's what she wanted, and what damage is it gonna do? I mean, I don't. Yes. Right. Yeah. Yeah. And that's not necessary. Right. Right. Yeah. Okay. Yeah. Yes. Yeah, that sounds good. If you need any help, let me know. Yeah, everything else is good. I mean, it's uneventful, which is excellent. Yes, I will take that. Yeah, I do, but I don't anticipate that changing. We found somewhere to put it, so we cleaned out the closet in the office, which is actually a really big closet. We're just putting her stuff in there. It's an it's an inconvenience, but yeah, exactly. I mean that there's been stuff in that closet the whole time we've lived there, and I have no idea what was in there. So yes, yeah. So I mean, it'll be fine. Eventually, she'll decide she wants her stuff back, or I will decide to take it and throw it away or burn it or something if she doesn't come collect it. I mean, okay, that's what the child wanted to do. So, and I understand the frustration. I get it. So, but I, you know, we'll try not to do that. Not that any of it's that important. I mean, the stuff she had shipped is not. It's like old glasses and towels that she never uses. So I don't even know why it's there, but whatever. It's not my stuff. It's not my place to judge. Right. Yeah. And hopefully someday it will go where it's not in my house. But yeah. No. I mean and it was causing me way too much energy trying to figure out how to get it out of the house. This is just the easier, softer way, and it's not causing any damage to do this. So yes. Yay. Yeah. But again, it's a couple more weeks, and then this term is over, and then we're going to Chicago for a couple days, and then it starts all over again. Yeah. Well, and we're not really. I found some weird interactive prints thing, and we're going to see that. So I think it'll be interesting because I think it's going to be similar to the Van Gogh one that we went and saw, and that was it was fabulous. I loved it. Yeah, it was really fun. It was a nice experience. They had lots of stuff you could buy, which I'm always a fan of that. So yeah, but Mike and I have never been there together, so I think it'll be an interesting trip for us. Yes, yes, they are coming right before school starts. But hey, yeah, I figure it's the last vacation they're going to get before school starts. So yeah, tomorrow morning I work until 10, and then I'm going to the club. I go Fridays to the club. And I wasn't planning on it now. Okay, I can do that. Awesome. I love you too. Bye. Again, I apologize for having to pause like that. I having my car detailed and I my phone was ringing. So that's the structure that we come up with for this. The table that's here is not provided in the handouts. It was meant to be, but it's not. And so this is what you're going to see on the test when you have to do this. I do not expect you to remember any of this material. This is stuff that you should be able to reference. So what you're looking at, and we'll zoom in a little bit, what you're looking at is the number of bonding electrons and the number of lone pairs. Okay, so this is the number of pairs. So since we have 3 bonding pairs, that means we need to be looking somewhere where it says 3, and we have 2 non-bonding pairs. We want to find the 3, 2. And look, it gives an example of ClF3. It says that the bond angles are approximately 90 degrees, that the geometry of the electron pairs is trigonal bipyramidal. That means that we have 3 in the plane, 1 above and 1 below. Now it turns out, because the non-bonding pairs take up more physical space, that we're going to have a non-bonding pair below the plane, 1 above the plane, the chlorine in the middle, and then the 3 fluorines are going to be around that in the plane. So that's what we're looking at there. Now, if we talk about only the molecules, okay, which is how we get to our geometry or molecular geometry, we're only talking about where those 3 fluorines exist. And so they're all 3 in this plane, and that's called T-shaped. Okay, so that's the name of that. It's listed as an AB2E3. All right, not that you need to know that. That part I don't really care about. But that's how that's arrived at. Okay, now we're going to continue to do this, but I want to go back and talk a little bit about why does it arrange in this way? Why is it that this is what we see? And the reason that that's what it is, we use something called the valence shell electron pair repulsion method. Now, there are 2 ways of looking at molecular geometries. This is the one that we're going to talk about here. There is another one that's called molecular orbital theory. We are not going to deal with that, okay? Now, the valence shell is the outermost electron-occupied shell of an atom, and it contains the electrons that are usually involved in bonding. So it's the ones that are the furthest away from the nucleus. Double and triple bonds are considered the same as a single bond when we talk about this method, okay? So just because there are more electrons there, it doesn't matter. They have to be localized in the same space. So they're considered the same. So they do take up more space, but we consider them as if they do not. If there are 2 or more resonant structures, we can use any of them to determine the geometry. Okay, the formal charges are not shown when we talk about molecular geometry. We can use any of those resonance structures because they're all partially correct. So to determine the geometry of the molecule, we need to be able to answer 2 questions. How many bonds are on the central atom, and how many lone pairs are on the central atom? Now, valence shell electron pair repulsion says that we want the maximum amount of space between all pairs of electrons. And so we're going to distribute in 3 dimensions around that central atom in a way that we minimize the repulsion between those electron pairs. That's what this is talking about. And the structures that we see when we do this are listed on this table. So we have something like trigonal planar, another trigonal planar. So the electron geometry is trigonal planar for both the trigonal planar and the bent molecule. Okay, now this is a little hard to read because it's sideways, which is why I've been talking to the other one, which is this one right here. So these are the general structures that we're going to be talking about. Do I expect you to know what those structure names are? I expect you to be able to find them in the table. Yes. I need you to know the difference between the electron pair geometry and the molecular geometry. So this first column is the electron pair geometry of the electron pairs. And the second one is the molecular geometry. Okay, so we're only considering the atoms, and that's the difference. In the first case, we're taking into account how everything is arranged, the lone pairs and the bonding pairs. In the second case, we're only talking about the bonding pairs and how those are arranged around the molecule. All right, so it's as if we're reviewing only the molecules without the presence of the lone pairs, but the lone pairs are still determining where the molecules exist. Okay, so that's how we talk about that. Now, we're going to go through a bunch of examples that are going to show you how we do this. In each case, we're going to draw the electron structure, just as I've done here, to practice that for you guys. We should be talking about formal charges as well, so I'm going to walk through the formal charges so that you guys can see that. because that's one of the things you need to be able to do. So I'm going to show you that again, and then we're going to show you, based on that structure, what that's going to look like and how we pull that information out of the table. Right. So let's talk about the formal charges on this molecule that we've already drawn. So we're looking at this particular guy right here. We have two things on here. We have a fluorine and a chlorine. All right. Now, in each case, our formal charge, Fc, is equal to the valence electrons, the number of valence electrons that it has, minus half of the bonding electrons, and I'll show you an example in just a second, minus the non-bonding electrons. Okay, so if we're talking about fluorine, it has 7 valence electrons. We determined that up here when we were talking about how many electrons were present. So we know that it has 7 valence electrons that we need to be able to deal with. We're then going to subtract half of the bonding electrons. So essentially, if we're talking about this fluorine right here, change my pen out, we're pretending that only one of those electrons belongs to the fluorine. But we have to take both of them into account, so that we count the number of electrons that are in that bond and say one of them belongs to the fluorine. So that's why it's 1/2 of the 2 electrons in the bond. Okay, if we had more bonds, we do more numbers. And then we subtract the non-bonding pairs. So the 2, 4, 6 non-bonding pairs that are on this fluorine, we're going to subtract those 6 as well. Now, that's going to give me 7 minus 1 minus 6, which is 0. 0 is an excellent formal charge. All right. It tells us that we have accounted for all of the electrons that we needed to account for, and we have no extras or weirdness in terms of where they are. Now, if we have negatives in terms of formal charge, those negatives need to occur on the most electronegative atom in that particular structure to make things happy. So that's one of the things that we need to look at formal charge for. Now let's talk about chlorine. We know that chlorine also has 7 valence electrons. We're going to take half of the bonding electrons. When we talk about the chlorine, he has 2, 4, 6 bonding electrons because there's 3 bonds, each containing 2 electrons, so 6 total. And then we're going to subtract the lone pairs that are assigned to the chlorine, so the 2 and the 4. So there are 2 lone pairs, 4 electrons. So half of the 6 is 3 minus 4, that's 7. That means that my formal charge on each chlorine is also 0. So I have no formal charge in this particular molecule, which is great. We want to minimize the formal charge that exists. So if we can get to a state where we have no formal charge on anything, that's ideal. All right. Do we have questions, comments, problems about any of the stuff that I drew, any of this, how we arrived at any of this, what all of this means? If you have questions, please let me know. It is important that you be able to go from the number of electrons to the Lewis structure for that molecule using this process, total number of electrons, to put in the bonding electrons, assign the non-bonding electrons, anything that's left goes as lone pairs on the central atom, and then we determine if that's a good structure or not based on the formal charges. Okay, so if we'd run into formal charges here, we'd have to consider, is that a good place for them to be or is it not? Do we need to move some of those electrons to try and minimize that? That's the kind of thing that we'd be talking about. Okay, I'm going to go back to my slides. All right, so the next thing that we're going to talk about, we need to talk about this difference between electron and molecular geometries. So remember that I said that there were electron geometries that took into account all of the electrons, the non-bonding and the bonding. And then there are molecular geometries where we only consider the bonding electrons. So if we're talking about this molecule right here, when we talk about the electron geometry, it needs to take into account this bond, and this bond, those 3 bonds, and these 2 lone pairs. So we need to account for all 5 of those. In the molecular case, we need to account for all 3 of these in the geometry that they exist in with these 2 electron pairs on them. But we only want to name the 3 things that are here. Okay, that's how we get to this table where we have 3 bonding pairs and 2 non-bonding pairs, which leaves us with an example of CF3, and that's T-shaped. Now, this takes into account all 5, 1, 2, 3, 4, 5, for that electron pair geometry, which is trigonal bipyramidal. That's what the 5 is called. Okay, so if we have 5 with nothing on it, that's a trigonal bipyramidal structure. That's right here. Okay, but as we take 2 of those molecules off and leave this as the trigonal bipyramidal here, we end up with this being T-shaped. So we have 1, 2, 3 of them in this T shape. That's how that comes about. So if we were to list the electron pair geometry, sorry, I need to get over here. Electron pair, that's trigonal bipyramidal. And my molecular geometry is T-shaped. And if they were ask me, then I would say in this particular case that each bond angle is approximately 90 degrees. Bear with me just a moment, I apologize. Okay, so that would take care of the majority of the questions that we would get around this kind of thing. So electron pair geometry, molecular geometry, bond angles, how many bonding pairs, how many non-bonding pairs, those kinds of questions would be what we would expect on a test. So we would expect that you would get a molecule, or my expectation is that you would get a molecule, say, and okay, draw me a Lewis structure. Tell me how many bonding pairs are there? How many non-bonding pairs are there? What's the molecular geometry? What's the electron pair geometry? What are the bond angles? What's the formal charge on everything on a particular atom? I mean, there are a number of variations that we could see for that. Okay, so that's what we're talking about there. As far as other things go, let's see what else we can talk about. And what I'm going to do now is try and clear this up a little bit. You can tell I don't use this thing very often. Okay, so that's at least better. All right. So that takes us through that CLF3 example. We can take a look at some other examples as we move forward. Now, each of these are presented as going through that chart as it exists. So we're going to go, and it's not this particular chart in this order. It's in the order of the chart here. So that's the order which we're going to walk through this. So you're going to see molecules for each that line up with each of these examples. I'll walk you through on the chart that you'll have on the test to see what those look like and where they are. Okay. So the first thing we're going to talk about is a linear structure. This is, again, electron pair geometry is linear. The molecular geometry is linear. This has two groups, like two electron pair groups. So remember, this may be a double bond, but it's only considered as one. Okay. So the structure that we're looking at here is CO2. So CO2, I have carbon. Carbon has 4 valence electrons. Each oxygen has 6. There are 2 of them. That gives me a total of 12. Plus the 4, 16 total. So I'm going to put a carbon here, an oxygen here, and an oxygen here. I'm going to put one bond in between each of them. That takes out 4 of the electrons. And at least we have 12 that I need to deal with. I then put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because I fill the octets for the outside first. That leaves me with no additional electrons. Okay, so in theory, I'm done, right? Except I'm not. And I know that I'm not because I don't have an octet around my central atom. So I can't leave it the way that it is. What I need to do is try and find some way to take the electrons that exist in this molecule and give carbon a stable octet. So I'm going to take 2 of the electrons. I'm trying to pick up a different color here. So 2 of the electrons, and I'm going to take them from the lone pair status and I'm going to move them in. I'm actually going to do this eventually on both sides, but I'm going to show you what it looks like if I do this one first. Now I have 1, 2, 3, 4 electrons left, and I've just moved 2 of them up because it's more aesthetically pleasing to me if I do it like that. I then have 1, 2, 3, 4, 5, 6 electrons around the oxygen. Now notice I have the same number of electrons that I still had before. So I've still got all of my electrons distributed, but they're now in a different arrangement. Now if I look, oh, and let's do this. Sorry. Formal charge for my carbon here. Formal charge on the carbon, there are 4 valence electrons minus half of the bonding electrons, which there are 4 of them. 2 in each bond, 2 bonds, and then no lone pairs. So that gives me a formal charge of +2. And if I do the same for my oxygens, as they're written here, I have 6 that I'm supposed to have. I have half of the 2 electrons in one bond minus the 6. That gives me a -1 charge for both of them. Okay, now that means that my net formal charge is 0. Okay, but I do have formal charges on both of these atoms, which is not what I'm looking for. I want to minimize that, which is part of why we're moving these things. Okay, if we do the same here, and I'm going to label this just so we can tell the difference. This is carbon 1 and this is carbon 2, or oxygen 1 and oxygen 2, I apologize. We're going to do our formal charge. Again, carbon is 4 valence electrons. We're going to subtract half of the 2, 4, 6 that are in the bonds, which gives me 3, and there are no bonding, so I then have a charge of +1. My 1 oxygen is going to be exactly the same as it was, so 6 minus the 1 half of the 2 minus 6 equals -1, and my other oxygen is now going to be half of the 4 minus the 2, 4, which gives me 0. Okay, so again, my net charge is perfectly fine, but my oxygen is not completely happy. Okay, even though he has a negative charge, it still has a charge. And my carbon still does not have a complete octet. He only has 6 electrons around him. So he's not happy. So we're going to do the same sort of thing that we did before. And now I'm going to try this again. And I'm going to take another lone pair and pull that in here. So we're going to end up with the same thing that we did before on both sides. And if we look at the formal charge here, our carbon should have 4. It's half of the 2, 4, 6, 8 minus 0 non-bonding gives me 0 for that one. That's my carbon. Both oxygens are the same, so I only have to consider them once. There should be 6. Half of the 2, 4 minus the 4 non-bonding is also 0. So there's no formal charge on that. So I know that that's the best structure that I can come up with. And that's how we arrived at the structure that we're looking at here. Okay, so again, I have drawn my geometry. Carbon, 4 electrons, oxygen, each of them with 6 electrons, gives me a total of 16 that I need to distribute. I start with a bond between each of the carbon and the oxygens. That takes away 4 of those electrons, and then left with 12, which are distributed around each of the oxygens, 6 on each. And that leaves with no more electrons that need to be distributed. Looking at this structure, however, I see a lot of formal charge. So I want to minimize that formal charge. And I start by moving 1 pair of electrons to do that. That 1 pair of electrons that I move then gives me a double bond here. I then look at my formal charges and I still have a +1 on my carbon. He still only has 6 electrons around him. And I have a -1 on the oxygen on this side, the one that's single bonded. So then I move another pair of electrons into this double bond. And that gives me a structure where I have zero formal charge. All of my electrons are distributed and everybody's happy. Okay, so that's how I get there. Now, once I get there, looking at that particular arrangement, I have around my central atom, I have 2 sets of bonding pairs. So this is considered as 1 and 2. Remember that the double bonds are considered the same as the single bonds. So we have 2. We go look at our table, and we'll look at the one that's turned this way. We have 2 bonding pairs, no lone pairs. An example of this is BCl2. My bond angles are 180 degrees. This is a linear structure. And the geometry is still linear because I have no non-bonding pairs, so I have to list all of them. And this is my 3D shape. It's linear. Okay, and that's what we're showing right here. Okay, so we have 180 degrees between each oxygen and each carbon. This is a molecular geometry of linear and an electron pair geometry of linear. Both of those are the same since I have no lone pairs. Okay, so that's that first structure that we're going to talk about. Now, let's see if we can clean this up a little bit. My world does not love me today. Okay. And I may try this with the mouse because that may work easier. We now want to talk about BF3. So again, B, F. And of course, there's 3 Fs. So F, remember, has 7 valence electrons. There are 3 of them. Gives me 21 from the fluorine. Now, boron exists in my table as number 5. So he's in that group 3A, which means he has 3 valence electrons that we are dealing with. So we're going to write this as 3. There's 1 of them. That gives me a total of 3 there. And that means my total is 24. Awesome possum, I've got 24 I need to deal with. Now, how do I deal with my 24? I take my boron, since he's my one that's written first, he goes in the middle. I have 3 Fs that are going to go around him. And there's no real rhyme or reason to why I put them where I put them. It's just drawing them. I mean, you will notice that as I continue to move things, we end up with more. It looks more similar to the electron pair geometries and the molecular geometries, and that's just because of my familiarity with them. But there's no rhyme or reason to why they get drawn the way they're drawn. Now I need to bond between each of these. So I have 2, 4, 6 electrons that are taken up with that. And if my happy math is correct, that should be 18. I'm not great at subtraction, so hopefully I don't screw that up. Now, I need to fulfill the octets on each of the fluorines. So each one of them is going to need 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have 6 on each fluorine. That means that each fluorine now has an octet. 6 times 3 is 18. So that means that I've distributed all of my electrons. Now, boron is not completely happy, and I know that because it's not a full octet, but what I can't do with boron is pull one of these in here and make a double bond. Why can't I do that? Because there's nowhere for me to put those electrons to be able to do that. It's because of where it exists in the periodic table. So being in row 2, I cannot move that into a double bond. Only things in rows 3 down can do that. Boron can't. So this is a structure that we end up with. Since I have 3 bonding pairs and no lone pairs, then we're looking at a situation. 3 bonding, no lone, BF3 is an example of that. That's trigonal planar. for the electron geometry and trigonal planar for the molecular geometry. Both of them are going to be trigonal planar because I have no lone pairs. Sorry, that's a really ugly one. Electron geometry is trigonal planar. This is a fun pattern. And my molecular geometry is going to be exactly the same because there are no lone pairs. And I'm not going to write that again. I'm just going to put an arrow there. Okay. If they ask me about my bond angles on this particular molecule based on my table right here, I'm looking at 120 degrees. Okay. Questions, comments, problems on how we got to that structure? Hopefully not. But again, this starts with how do I practice counting the electrons, getting from the electrons to a Lewis structure, from the Lewis structure to see if I can move anything. Oh, and that's the other thing I didn't do. I apologize. Let me see if I can move this. Nope. Try one more time. I don't know if it's going to let me move it. So. Nope. So let me do this. Formal charge B and formal charge on F. So boron should have 3 valence electrons. Each fluorine should have 7. I'm going to subtract half of the bonding pairs, so the 2, 4, half of the 6. And I have no lone pairs. So that's going to give me a formal charge of 0 for my boron. And fluorine should be 7. I'm going to subtract half of the bonding pair for that. And then minus the 2, 4, 6 in lone pairs. And that gives me a 0 for each of those. So I told you that we couldn't make a double bond with the boron. In addition, I have no formal charge there, so I can't move anything any further. That's your biggest indicator that you need to change things, is if your formal charge is weird. Okay, so since there's no formal charge here, we are done. This is the structure that we're looking at. Okay, questions, comments, problems? Hopefully not, but that's how we end up with BF3 in that particular geometry. And of course, if you do have questions, comments, problems, please let me know. So pull my slides back up and let's go to our next example. So this is called bent. What we're looking at is O3 minus. Now O3 minus is one of the things that we drew the last time we talked about this. Now remember that oxygen has 6 valence electrons. There are 3 of them. And that gives me a total of 18. Now, I put an oxygen, an oxygen, and an oxygen. I draw one bond and one bond, and that gives me 4 that have been distributed. And that leaves me with 14 electrons. Okay, so now we have 14 that we have left to distribute. I'm going to take 2, 4, 6 there, 2, 4, 6 there to fulfill the octets on the outside oxygens. That takes up 12. That leaves me with 2 that I have to deal with. I'm going to take those 2 and put them on the center. So each oxygen on the outside has a full octet. So the 6 lone electrons in the lone pairs and the 2 electrons that are in the bonding pairs. My central oxygen, on the other hand, has the 2 from the lone pairs and only 4 that it's sharing. So there's not a full octet around that central. Okay, even though I've distributed all of my electrons. So I've now distributed everything because I forgot to do that. Let's look at the formal charges if we talk about this particular thing we're looking at here. Formal charge. And we're going to do the oxygens on the outside as 1, and the oxygens on the inside. The oxygen on the inside is 2. So I know that each one should have 6. That's my number of valence. I subtract for the ones on the outside half of the 2 that are in the bond minus the 6 non-bonding, and that gives each one of those a -1. All right. If I look at the one in the center, on the other hand, I subtract half of the 4 minus 2. So half of the 4 is 2 minus 2. That gives me a plus 2. Not ideal. Okay, so I now have a plus 2 formal charge here and a -1 on each end. All right. I don't like to draw them like this, but that's okay. That's what you're looking at in here. Now, that's not an ideal situation. So let's see what we can do to try and remedy that situation. If I take one of these pairs of electrons off of this oxygen and pull it into a double bond right here, I then end up with an oxygen, a double bond, an oxygen, a single bond, an oxygen, and then one, two, three, 4 on that one, 2 on that one, 1, 2, 3, 4, 5, 6. So I still have the same number of electrons that I had before, but I now have a situation where I've moved 2 of these electrons from here to here. That changes this charge here so that it's now a different value. And let's calculate what those values are. So formal charge, we're now going to call that 1, 2, and 3 because each of them is different. So I'm just going to talk about them as 1, 2, and 3 because it doesn't really matter how I do this. I know that I have 6 electrons for each of them that I'm supposed to deal with. Number of valence is the same for all of them. On one, I have 2, 4 electrons, half of which go to that particular oxygen. So I have 2 bonds, so that's 4. And then I have 2, 4 that are non-bonded. So the formal charge there is 0. So this guy is 0. If I look at the second one, I have half of the 2, 4, 6 minus 2, which gives me a plus 1. And if I take a look at the third one, we're going to take half of the 2 that are there, subtract the 6, it gives me a -1 there. And that's the structure that makes me the happiest, okay? Because if I pull another electron pair from here, right? If we were to do that, then that would require oxygen to have more than an octet. Oxygen being the second row, he does not have d orbitals that we can work with to expand his octet. So there's no way that we can make another double bond for that particular oxygen. So it's just not possible for us to do that. So this is a structure that we're looking at. That means that my central atom has 2 sets of bonding pairs and 1 set of non-bonding pairs. So 2 bonding, 1 non-bonding, SO2, okay, is an example, and that's bent or V-shaped, okay? And so we end up with this bent structure, which is what we were looking at here, bent like this. And my lone pair is up off of this central atom, okay? This bond angle is less than 120 degrees, and that's over here, so I'm not going to rewrite it. So that's what we're looking at for this particular structure. So that's how I got to that structure, and that's why it exists the way that it does. Questions, comments, problems on that? Again, hopefully not, but if you do have any questions, comments, problems, please let me know. Email, phone, whatever you need to do to get a hold of me so that we can talk about whatever it is that you don't understand. Okay. So let's move on to our next structure. So now we're looking at our next structure. This is TiCl4. TiCl4. Okay. So titanium, Ti, is number 22. That means that he has 4 electrons that he can bond with. Now, 2 of those are in the 4s2, and 2 of them are in 3d. It's not normal for that to happen, but it can happen in this particular case. All right. So there are 7 on each of those. That is then going to give, and there are 4 of them. 7 times 4 is 28. Add the 4 to that, that gives me 32. Put Ti in the center. Cl, 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 Cl. My C's don't look very good today. 2, 4, 6, 8. because my math sucks. 32 minus 8 is 24. Just wanted to make sure that my head was correct. I'm not always good with subtraction. 24. Now, fulfill the octets on the chlorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we can talk about Ti and Cl, both of these being formal charge. Ti should have 4. Take half of the 8 that surround it. There are no non-bonding pairs. And that gives me a 0 for the Ti. For our Cls, we should have 7. I can take half of the 2 that are in the bond minus the 6 that are associated with each of those, and it gives me a 0 on those. So everybody has no charge. This is the best structure that I can do. Ti has a stable octet, so this is a happy place for me to be. Okay, I've calculated everything that I'm supposed to calculate. Go, awesome. Now, having said all of that, if I wanted to look at my electron pair geometry, I have 4 bonds that exist around this titanium and no lone pairs. So 4 bonds, no lone pairs. An example is CH4. That is a tetrahedral structure. Because all of them are bonding, that is also tetrahedral. So my electron geometry and my molecular geometry are both tetrahedral. All right, so that gives me the structure that I'm looking at. Okay, everybody's happy. Tetrahedral, my bond angles, just in case anybody wants to know, in a tetrahedral structure are 109.5. And it may seem like that rolled off my tongue very, very easily. It did. If you take organic chemistry, you will become very familiar with tetrahedral structures and their bond angles of 109.5. Okay, so that's our structure for TiCl4. Questions, comments, problems on TiCl4? I hope not. Again, this is a tetrahedral. Everybody's tetrahedral there. Awesome possum. We're good. Yay! Let's talk about our next structure. So now we're going to move from the structure that we were just looking at to NH3. So my nitrogen has 5 valence electrons. Each hydrogen has 1. Gives me a total of 8 that I need to deal with. Nitrogen in the middle, hydrogen on each, a couple of hydrogens around it, 1 bond for each of those. 2, 4, 6 are taken up in that. That leaves me with 2. Those 2 are going to end up as a lone pair on the nitrogen. Now, if I look at my formal charge for everything, nitrogen should have 5 electrons. Hydrogen should have 1. I'm going to subtract from the nitrogen half of the 2, 4, 6 electrons that exist in the bonds minus the lone pair, which gives me a formal charge of 0. Each hydrogen should have 1. I'm going to subtract half of the 2 electrons in the bond, and there are no lone pairs there, so that gives me 0 as well. So that's my structure that I'm looking at for NH3. So this is similar to what we looked at for the last one. We have 4 things surrounding that nitrogen, but instead of having 4 of them be bonding, we've changed one of them to non-bonding. So what that means is that my electron pair geometry is still tetrahedral because I still have 4 things that I need to deal with. But my molecular geometry has now changed. And so if we come down and we look with 3 bonding pairs and 1 non-bonding pair, my example is NH3, my electron pair geometry is tetrahedral, as I stated, and it's now listed this structure as trigonal pyramidal. I hate that word. So trigonal pyramidal. Okay. So we have essentially these 3 guys that are sitting like this, and the electron pair, the lone pair, is sticking up in the air. But the 3 that we have to describe are the 3 that are sitting like that. So that's that trigonal pyramidal structure that we're looking at here. Okay. So that's how we describe that. Those are our formal charges. This is our Lewis structure. This is the accounting for all of our electrons. Everybody's happy. Now, what is our bond angle in this? Well, our bond angle, when we talk about this, instead of being 109.5, that electron, the non-bonding pair at the top, pushes everything down a little bit, takes up more physical space, and so it's less than 109.5. That's an acceptable answer. Or 107.5 is what it technically lists, because we do see about 2 degrees of change because of the presence of the non-bonding pair. Okay, so that's that guy right there. Awesome possum. That's our NH3. Woohoo! Okay, there are only what? 1, 2, 3, 4, 5, 6, 7, 8 more to go. Woohoo! Yay! Let's go ahead and clean this up, and then we will talk about SnCl2. SnCl. Each SN, I'm not sure about. Each Cl, I know is 7. There are 2 of them. That gives me 14 that I need to deal with for the SnCl2. Sn, we need to find in our periodic table. Where is my Sn? Sn is number 50, which puts him underneath carbon, which indicates that he should have 4 valence electrons to deal with. It gives me a total of 18. 18 electrons that I need to distribute. My Sn is going to go in the center. I'm going to have chlorine on either side. I'm going to draw 1 bond in between. That takes out my 4 electrons, which leaves me with 14 again. Yahoo! And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Total of 12. All right, guys, I apologize for that. I started to draw the SNCL2 and realized that I had made a mistake and I had the wrong number of electrons around it. So I needed to find you an actual number of electron groups that was 4 and bonding groups was 2 with 2 lone pairs. So obviously the most relevant for that is water. And we're going to go ahead and draw the water structure here. So each of our hydrogens has 1 electron. There are 2 of them. So that gives me a total of 2. My oxygen has 6 electrons. And that means I have a total of 8 after I add the 6 and the 2. Put my oxygen in the center, an H over here, and an H over here. Draw 1 bond there. And then that leaves me with 2, 4. So I've taken off 4 of them. That leaves me with 4 electrons I need to distribute. I'm going to put 1, 2, 3, 4 around my oxygen. I have an octet around the oxygen, a duet around each of the hydrogens. I can talk about the formal charge for each of these species. H and O. H should have 1 electron. We subtract half of the bonding electrons. There are 2 of them. There are no lone pairs. So that's going to be 0. My oxygen should have 6. I subtract half of the 4 from the 2 bonds. And then I subtract my 4 in the lone pairs, and that gives me 0. Okay, so that's the structure that we're looking at here. I have 2 bonds, 2 lone pairs on the oxygen. If I look for 2 bonding pairs, 4 total, 2 bonding, 2 non-bonding, my example is H2O. That has a 104.5 degree angle. So again, we've gone 4 degrees down from the 109.5. Its electron pair geometry is still listed as tetrahedral because there's still 4 things around it. But my molecular geometry only consists of the 2, H2 and O. And of course, that's going to be bent because I have these two sets of lone pairs. So for what we're looking at is this H2O right here, we see that no matter which way I organize this thing, 2 of them being lone pairs and 2 of them being bonding, it's going to be bent. Okay. So that's what we're talking about in terms of that geometry. And my bond angle here is either a lot less than 109.5, which is an acceptable answer, or 104.5, as read directly from the table. Okay, so again, you need to recognize that it's less than it would be if there were no lone pairs present, but it doesn't really matter that you know exactly how much it is, so either one of those answers would be considered acceptable. Okay, hopefully that takes care of that, and I will get these updated slides onto D12 for you guys. Okay, let's talk about our next molecule. So the next thing we're going to talk about is PF5. On PF5, I have a phosphorus and I have a fluorine. My phosphorus is directly under nitrogen. That means he has 5 valence electrons. So 5 from the F. I have 7 electrons on each of the fluorines. There are 5 of them for a total of 35 there, which gives me 40 that I then need to distribute in total. I will write my P in the middle because he's written first. I have an F, have an F, have an F, and I have an F. Again, no real rhyme or reason for where I drew them. Draw one bond between each P and the F. So 2, 4, 6, 8, 10 electrons taken up there from those bonds. That leaves me with 30 that I need to distribute. I'm gonna, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1. Oops. Can't draw today. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 are on each of those. 6 times 5 is 30. So that takes out the rest of those electrons, and that leaves you with a 0. Okay, awesome. Let's talk about formal charge. P and for F. So phosphorus should have 5 electrons. Each fluorine should have 7. They're all the same, so I'm going to consider them all at the same time. There's no reason to consider them differently. For the phosphorus, I'm going to take half of the bonding electrons. So 2, 4, 6, 8, 10. Minus 0 non-bonding. And that gives me a formal charge of 0. I have 7 electrons. I'm then going to take half of the bonding electrons. There are 2 bonding electrons between each P and F. I have 6 non-bonding electrons in each. So that gives me a formal charge of 0 for the F as well. All right, no formal charges, happy structures. I have 5 things that are arranged around this phosphorus. So if I want to talk about my Mg and we'll talk about Eg first, so electron geometry, and then the molecular geometry. Both of them are going to be the same because I have no non-bonding electrons. I now have a case where I have 5 things around my central atom. My PCl5 is what it gives me. It says trigonal bipyramidal. Okay, and both of them are trigonal bipyramidal. What it says is that the bond angles in the plane are 120 degrees apart because there are 3 things in the plane. And then there are 90 degrees between the plane and what's perpendicular to it. So I have 2 bond angles. One is 120 and one is 90. Technically, both of those should be listed because they are not consistent. Okay, so that's what I would see for that particular structure. Okay, questions, comments, problems on that? Again, I hope not, but that is my PF5. Okay, I swear we're reaching the end. It takes forever, I know. So now we're going to talk about SF4. So S and F. Again, the F each has 7. There are 4 of them. I've gotten a little lazy, so I'm not writing E anymore. That gives me 28 to deal with from the fluorine. My sulfur is right underneath oxygen, so he should have 6 electrons that I need to deal with. 6 and 8 is 34. I put my sulfur in the middle. I have a fluorine, a fluorine, a fluorine, and a fluorine. Again, no real rhyme or reason to where I put them. One bond in between each sulfur and each fluorine. 2, 4, 6, 8 taken up in that. Which means we have 26 electrons that I need to deal with. Again, just checking my math. 26. I'm going to put 1, 2, 3, 4, 5, 6 around each fluorine. Six times 4 is 24. We then have 2 left. And that means that those 2 are going to end up on my sulfur. I've now distributed all of my electrons. Now the question becomes, am I happy with the structure that I have? In order to answer that question, we're going to talk about formal charge. We'll do that for sulfur, and then fluorine, all of the F's are the same, so we can do that. Our sulfur should have 6 electrons. We're going to subtract from that half of the bonding electrons, so the 2, 4, 6, 8. And then subtract the non-bonding electrons, so 2, 4, 6. Happily, that gives me 0. My fluorine should have 7. I subtract half of the 2 bonding. And then subtract these 6 from the lone pairs. And that gives me 0 as well. Okay, awesome. Everybody has 0 charge. I'll have all of my electrons distributed. Cool. So everybody should be happy at this point. Now, we talk about our electron geometry, which, since we have 5 things around it, is still going to be that trigonal bipyramidal, right? And I'll show you that in a second. And sadly, my handwriting does not look much better when you see it in person. So, on our table, we had 5 with 0 was trigonal bipyramidal. So that's my electron geometry still. It's trigonal bipyramidal. But one of those is now a lone pair, and so we call that structure seesaw. Right? So that's that. My bond angles in my seesaw are listed as complex. What that means is that all of those ones that were down, okay, are going to be pushed a little bit. So it's going to be less than 90 degrees in between the perpendicular and the plane, and each one in the plane is going to be slightly squished as well. So it's just listed as complex, and that's perfectly fine as an answer. Okay. So that's my SF4. Sweet. Awesome, awesome. Let's move on. And again, questions, comments, problems are welcomed. If you have them, please let me know. Let's try and make this not complicated. So let's get you the answers that you need. All right, the next thing we're going to do is CLF3. So CL and F. They all have 7. So technically we could just do 7 times 4, which gives me 28, but I like to do it this way. So that way I've accounted for everything directly. Okay. So now I put my CL in the center. I'm going to have an F, an F, and an F that I need to contend with. I draw a bond, That gives me 2, 4, 6 that are taken care of. That leaves me with 22. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 3 is 18. That leaves me with 4 electrons that I still have to distribute. I'm going to put them all on the chlorine. So that takes care of my other 4. And that leaves me with 0. If I want to look at formal charge, Cl and F are different. So while they had the same number of valence electrons, they do not have the same number of bonding electrons. Chlorine has 2, 4, 6. And then it has 4 non-bonding electrons. So if I take half of the 6, that's 3, minus the 4 gives me 7, so that's 0. If I take my 7 for fluorine, half of the 2 from the bond, and the 6 from the lone pairs, that also gives me 0. Hooray! Nobody has formal charge. All of my electrons are put out there. Sweet! I've got my structure. Now, if I want to talk about, and I'm going to put this up here as opposed to where I've put it in the past, my electron geometry is still that trigonal biparameter. So that's what we've been talking about for all my stuff that has 5. It's messy. My molecular geometry, on the other hand, I now only have 3 components that I'm looking at. So what the hell am I going to call that? Well, if I have 3 bonding and 2 non-bonding, such as ClF3, I have an approximately 90-degree bond angle, trigonal bipyramidal electron geometry. It's listed again as T-shaped. Now, are the bonds exactly the same as they are in my other T-shaped? No, not exactly, but I still have this T structure, okay? So that's what we're talking about there, all right? All right. That means I should have 4 more. Cool, awesome, 4 more. We can do this. We will not pass out and die because we talked about all of these things, I swear. So what am I going to talk about next? My next is going to be XeF2. We're going to have an Xe and an F. My F, of course, has 7 electrons. There are 2 of them, so that's going to be total 14 that I need to deal with there. My Xe is a noble gas, so he should have 8 that go with him, correct? And if I add that, 8 and 14 should give me 22. Put my Xe in the middle, F on either side, draw 1 bond. That takes up 4 of those. That leaves me with 18 that I need to deal with. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 for a total of 12. That leaves me with 6 electrons that I need to distribute. And I go 1, 2, 3, 4, 5, 6. So I now have around my central atom 5 things. So my electron geometry is still going to be the trigonal bipyramid. And hopefully you're listening because I'm sure you can't read that. My molecular geometry, on the other hand, is going to be based on the 2 things that I can see. So shockingly, I would expect this to be linear. And if you look, if you have 2 bonding, 3 non-bonding, that is a linear structure. Now, is this exactly the same as what we've talked about before? The bond angles actually are because of the way that this works, but we have more electron geometry around it, so we have a more complicated structure. Okay, so this is very similar to what we talked about in the past, but this is another way that we get there. Okay, questions, comments, problems on XEF2? Hopefully not, but if there are, please let me know. You know the ways to get a hold of me: email, phone, uh, drop it in the office hours, talk to me. Let's see if we can sort it out. All right, 3 more. SF6. SF. Sulfur being under oxygen has 6 valence electrons. 7 for each F. There are 6. 6 times 7 is 24, if I'm not mistaken. I'm tired, so I'm going to check that. Oh, 6 times 7 is 40. 42. I can do math. Really, I can. This is why I have a calculator. We add the 6 to that. That gives me 48 that I need to distribute. We put our S in the middle. I have an F. 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 And I have an F. So 6 of them. Now there's not, again, a whole lot of rhyme or reason where I drew them. This is not a great representation of how they actually exist, but it'll pass. Draw one bond between each sulfur and each fluorine. That gives me 2, 4, 6, 8, 10, 12 electrons that have been dealt with there. 48 minus the 12 then leaves me with 36. You go 1, 2, 3, 4, 5, 6 on each fluorine. So 6 times 5 is 30. Okay, so we put our 6 valence electrons around each of the fluorines. There are 6 fluorines and 6 valence electrons for each. So that's 36 electrons because I can't do math. So that's my total. All right, that means I have none left to distribute. If I do my formal charge for F and for S, and we'll do S is 6 valence electrons. F has 7. And subtract half of the bonding in each. So for my sulfur, I'm going to subtract half of the 2, 4, 6, 8, 10, 12. And no lone pairs. And that gives me 0. For my fluorine, I'm going to subtract 2 of the half of the 2 in the one bond minus the 6 non-bonding. And that gives me 0 for that. So everybody's happy. Okay, fine. Now that we're not confused, we can be happy. Awesome possum. So I have 6 things around my sulfur. 6 no lone pairs. That means that this structure is called octahedral. Okay, octahedral. So my electron pair geometry is octahedral. My molecular geometry, since I have no lone pairs, is exactly the same. All right, so that's the structure that we're looking at. We have 4 in the plane, 1 above and 1 below. That's our structure, AB6. Our bond angles, just in case anybody asks, are 90 degrees. Woohoo! Awesome possum. So that's our SF6. Now remember, sulfur being in the 3rd row, he has those empty d orbitals that are not used. So we filled the 3s and part of the 3p, but we haven't filled those 3ds. They're available to expand the octet, and that's how we managed to get this to look that way. All right, so this does violate the octet rule. We have more than 8 electrons around it, and that's okay because we have the ability to do that. All right. So that's everybody for that. Ooh, and that is not what I wanted to do. Where did it go? Ah, there we are. All right. Let's go to our next one. 2 left. So this is XE F4O. That's what we're trying to draw. So I need to look at my XE, I need to look at my F, and I need to look at my O to see how many electrons I get from each. Now the XE, remember, is a noble gas, so he has 8 electrons that he's going to contribute. The F has 7, but there are 4 of those for a total of 28. Checking my math. My oxygen has 6, there's only 1 of them, so I'm going to add the additional 6 to that. And that gives me a total of 42 that I need to distribute. Now, XE is written first, so I'm going to put him in the center. That means I'm going to have a fluorine, a fluorine, a fluorine, and a fluorine, and then an oxygen out here. Now, to start, I'm going to draw 1 bond for each of them. So 5 items, 2 electrons, that takes 10 of those. Now, I need to fulfill the octets for everything around that center atom. So let's start with our fluorines. 1, 2, 4, 6 on each fluorine. So 6 or 4 times the 6 is 24. Which gives me 8 left over. Now, we do our oxygen, 2, 4, and 6 there. That leaves me with 2 more that I need to distribute. And so I can put those initially as a lone pair on the XE. Now, let's look at our formal charges. We'll do our XE, we'll do our O, and we'll do each of the Fs. Now, they're all the same F at this point. So let's start with our XE. XE should have 8 electrons. Subtract half of the bonding electrons. So 2, 4, 6, 8 minus the 2 non-bonding electrons. Okay. And that's going to give me a formal charge of 4 minus 2. So that's a plus 2. Because we're only subtracting the 6 from the 8. So that's a plus 2 there. My oxygen should have 6. I subtract half of the bonding electrons. There's one bond. So that's 1 from that. And then I subtract the 6 that are there. And that gives me a negative 1. And if I then do my fluorines, I still can't do math. 6, 8, 10. Because that's 10 electrons. So this should be a plus 1. Excellent. You're getting the real life experience of what it'd be like to be with me in class. So that should be a plus 1. My oxygen is minus 1. And my fluorine should have 7. We're going to have to subtract half of the bonding. There are 2 in that bond minus the 6 that are around it. So shockingly, that is going to be 0. So that means that I still have formal charge. That's not a great situation, right? We don't really want that. So how can I deal with that particular situation? Well, the way that I'm going to deal with that is because oxygen has a negative 1 charge and the Xe has a plus 1 charge. I'm going to take one of these pairs of electrons from the oxygen and pull them in here. Now, that means I'm going to change my structure, and I'm going to erase so that I can show this a little better, a little cleaner. And then we'll recalculate our formal charge. So that means that I'm going to end up with this structure right here. And of course, if I move my other lone pairs just to make me happy. That means my formal charge on my Xe is now going to change. So we're going to have the 8 minus half of the 2, 4, 6, 8, 10, 12 minus the 2. So half of the 12 is going to be 6 minus 2, which gives me 0. Some possum. And our oxygen, we're going to have 6 minus half of the 2 minus, instead of 6, we're going to have minus 4. And it's not 2 anymore, it's 4. Duh. Because I moved them from there, from the lone pair to the bonding pair. So half of the 4 gives me 2, minus the 4 gives me 0. So all of my charges are 0. Yay! No formal charge. Yippee skippy. Let's talk about our electron geometry and our molecular geometry. And then I'll put my bond angles up here. So our electron geometry, I still have 1, 2, 3, 4, 5, 6 things that I need to account for around this thing. That means I'm still looking at an octahedral base because there's still 6. So I still have 6 of them. There's 1, 2, 3, 4, 5 bonds, because we consider the double as 1. 5 bonds, 1 non-bond, which looks like BRF5. That's called a square pyramid. Okay. My bond angles are approximately 90 degrees. Or not quite, but that's okay. And that's what we're looking at there. Okay, so remember a couple of things here. One, we can't forget that there's lone pairs here. We have to deal with that when we look at this thing here, because there are 5 bonding and 1 non-bonding. So I need to make sure that I'm down here and not just in the 5. Okay. The other thing that we need to remember is that this double bond is treated as a single bond. Okay, and when we talk about this geometry. So that's what we're looking at for geometry there. Okay. Woohoo! One more. Hooray! One more. We can do this. It's exhausting, I know. So, our one more that we're going to talk about is XEF4. So that's the one we're going to talk about. So we're going to have an XE, we're going to have an F, and there are going to be 4 of those. The XE has 8 electrons. The F has 7. There are 4 of them. 7 times 4. 7 times 4 is 28. Gives me 36 that I need to deal with in total. I'm going to put my XE here. And just for kicks, I'm going to put my FEs around my cardinal points. Or my Fs, I apologize. 1 bond for each. So 2, 4, 6, 8. Let's see with 28 that I need to deal with. 1, 2, 3, 4, 5, 6 on each fluorine. Six times 4 is 24. At least we get 4 more. And I'm going to put 1 there, 1 lone pair there, and 1 lone pair there. So that leaves me with a situation where I have 4 bonded, 2 non-bonded. So I still have 6 things around it. That means that I still have an electron geometry of octahedral. But my molecular geometry is only going to be considering the 4 that are there. So 4 bound, 2 non-bound, just like XEF4. We're still looking at approximately 90 degrees, an electron geometry of octahedral, and we call this square planar. Okay, so, and again, my angles, approximately 90 degrees. So that is everything. So again, all you're expected to do is be able to draw these, it sounds so simple. All you're expected to do is be able to draw these structures. Make sure that your structures are consistent. Oh, and your formal charge. Oops. Half of the 2, 4, 6, 8. Minus the 4 in the non-bonding gives me a 0 formal charge there. My fluorine, I have 7. I subtract half of the 2 that are in the bond. And then I subtract the 6 in the lone pair. That gives me a 0 as well. I apologize. So all you really need to be able to do is count the total number of valence electrons that need to be distributed. We distribute our electrons first by making bonds between each of the things that we have to put around that. So central atom, each of the things around it, we make 1 bond there. We take those electrons out. We then fulfill the octet for the exterior molecules, okay, and look to see how many electrons are left. Those electrons then go on the central atom. We then calculate the formal charge to see if we need to move electrons around. Okay, if we do, we do. Great, we do that. If we don't, we don't. That's okay too. Um, and then once we have a structure that we're happy with that has minimized our formal charge, then we look to see how many bonding pairs and how many non-bonding pairs we have. Then we use our table to figure out what does that structure look like. What is the electron pair geometry? What is the molecular geometry? And what are our bond angles? Okay, so that's what we're looking at for that particular set of things. All right, and those are the expectations, is that you can take the information from the bonding, the dot diagrams, um, through the resonance and formal charge. The only thing we really didn't talk about today was resonance. And again, resonance exists whenever we have the ability to have a multiple bond somewhere else, or we can move the electrons. And we can use any of those forms to determine molecular geometry. All right. But that's the kind of thing that we would be talking about. If you need more experience with looking at resonance, we talked about the O3 molecule, right? That was one of the things that we talked about. We saw that one of the oxygens had a double bond and one did not. So resonance structures for that, one would have the double bond on the left-hand side, one would have the double bond on the right-hand side. So that's my structures. And hopefully that takes care of everything that you guys need. Now, if you have any questions, comments, problems, anything at all, please let me know. This should be, I mean, it's less mathematical than everything else. So in theory, that should be easier, but it isn't always. So it depends on what kind of mind you have. For me, the math was a lot easier than doing the structures. Hopefully you guys are good. And if you're not, please let me know. I will talk to you again soon. Thanks, guys. Hope you have a good day.